Okay. All right. So I don't know. Linux stinks because stuff just stops working and you have to restart the stream, and then OBS kind of sucks on it. Linux is not all that it's cracked up to be. People are like, "Oh, Linux is the best." Linux is not the best, dude. I mean, yeah, obviously Linux is the best, but like, no, it's not. It's not the best, and it's not the best because it's just like it would be the best if we could get if more people used it. I guess that's like a dumb thing to say because obviously that's obviously, but all right, let's just get into this. I don't know what the heck we're even talking about. All right, so this is where we ended off the last time. So let me turn this on. Okay, so we have the astable clock, the monostable clock, and then the bistable clock, which just uses the SR. And I bought some single pole, double throw breadboard switches that'll come in a couple days so that we can improve this, in future projects. So that these, because this, I got some switches for this, and then I got some switches for this, so that at least we can get rid of this nastiness. Okay, so now it's time to do part 4. So part 4 is actually kind of a fun part of this because we're going to be using these logic chips. So, Ben...
In the last couple of videos, we built our 555 astable timer, which is putting out this oscillating clock pulse. And we built a monostable 555 timer circuit, which gives us a debounced push button switch. So we can push this and we get a nice clean debounced logic output here. And then we built our bistable circuit here, which also gives us a nice, debounced stable output for our toggle switch. Now what we need to do is just combine these 3 signals here into a single clock output signal for our clock circuit. And what we want is we want to, either output our oscillating signal or our manual signal, depending on which one we've selected over here. So I came up with a pretty simple circuit here that I think will do the trick. We've got our astable pulse input, which is this guy. We've got our select, which is the push button select. And then our manual pulse, of course, is the manual button that we can push there to get a manual pulse. And so what you see here is if our select is on, like this, then we have a 1 coming into this AND gate. And so our oscillator here, our astable oscillator, if it's a 1 or a 0, then that's just going to come out on this output here because a 1 and a 1 is a 1 and a 0 and a 1 is a 0. So that's just going to pass through. And then it's going to come down to this OR gate. And well, first, if we look at this other AND gate, our select here is inverted. And so we have a 0 coming into this AND gate. And so no matter what this is AND gate's always going to output a 0. So then over at this OR gate.
Yeah. Do it on this one. Not this one.
Oh, yeah, that's right.
We've got our clock pulse over here on this one input, and then we've got a 0
I added
on
this so that I can turn that off.
This other output. So again, that clock pulse just flows right through. So
okay, wait. So if the astable is high, then only if the select is high will this go to a 1. And if this is high, then this is low.
So if our select is on, then our output over here is going to be our clock pulse. If we turn the select off, then of course we have a 0 coming in here, and our clock pulse isn't going to come out. This AND gate's always just going to output a 0. On the other hand, our select, when we invert it here, we have a 1 here. And so if our manual pulse is a 1, then we get a 1 out on the other side. If our manual pulse is a 0, then we get a 0 out on the other side. And same thing with the OR gate. If we have a 0 or a 1 coming in here, we get a 0 or a 1 coming out here. This, of course, is always a 0. And so if we push our manual pulse, then we should see the manual pulse come out there when our select is off. So this looks like it should do everything we want. There's one other feature that I'm going to add to this, which is this halt line. And what this is, once we build the rest of the computer, we want to have a way for a program to be able to halt the computer programmatically. So maybe you have a program that computes something, and it gets to the end of the program, it outputs its result, and then it doesn't have any more work to do, and so it wants to halt the execution of the computer. There's nothing else to do. So what we'll have is we'll have a signal coming from the control module in the computer coming into the clock. So it'll just be another input into this clock circuit that says halt. And what that does is it should just turn off the clock. And so if there's no clock, then the computer's not going to do anything. And so what happens is we have this halt signal come in. It's normally going to be low, and so we invert it and get a 1. And then that 1 is just ANDed with our clock before, whether it's manual or the automatic clock. It's ANDed with that, and it comes out here. But when the halt goes high, if the program wants to halt execution, this goes high, then this goes low, and then you can see the final output over here of our AND gate is always going to be a 0. So there will be no clock, no matter whether you've got it in manual mode or using the oscillator, pushing the button. It doesn't matter. You're going to get nothing out there until we reset the computer, restart the program or something. So if we want to build this up, it looks like we've got a couple of inverters, 3 AND gates, and an OR gate. So what we could do is we could use the 74LS04. This has 6 inverters on it.
74LS04. I wish they would just say what the logic is. It's kind of stupid, man. Okay. 74LS04. Hex inverter. That's the knot. Okay.
Of course, we're only going to use 2 of them. We've got the 74LS08. And
74LS08. Okay. 08. And the 8 is what? 74LS08. This is the AND gate. Okay, so we get the 4 ANDs.
This has 4 AND gates on it. We're going to use 3 of those. And then the 74LS32. And this has 4 OR gates on it.
Okay, then the 32. This is the 47. The other 47. Okay. And then 32. All right.
Of course, we're only going to use 1 of them. A little bit inefficient to use these 3 chips. We're not using all 6 of these. We're not using all 4 of these. We're not using all 4 of these, but it should work. And one thing we could do is we could redraw this using different gates. For example, you could use all NAND gates or all NOR gates. Any logic circuit can be represented entirely in NAND gates, or it could be represented entirely in NOR gates. Those are called universal gates. And so just an example, I drew up an equivalent circuit here using just NAND gates. And so these are the same inputs. We've got our astable pulse, or select, our manual pulse.
NAND and NOR are the only... You can build any n-input Boolean function by wiring together only 2 input instances of them. That's very cool. So it's not just like 2 argument things. It's like any argument thing you can do with just NAND.
And then our halt line coming in. And I'm using just NAND gates. And so, for example, this NAND gate, I just tied the inputs together and it turns it into essentially an inverter. And so the nice thing about this is that, by using all NAND gates, it looks like we've got 1, 2, 3, 4, 5, 6, 7 gates, total 7 NAND gates. And so the 74LS00 chip has 4 NAND gates on it. So we could use just 2 of these. And so normally this would be a pretty good win here, right? We're using fewer parts, so it's going to take up less space, it's going to take less power, and it's going to be smaller and everything else. But we're not building, we're definitely not trying to optimize for the smallest computer possible here. And I think this circuit is easier to understand. It's going to be easier to troubleshoot. We're not trying to save space. We're not trying to save power. The cost of an extra chip is less than it's a 50 cents or something. I don't know whatever these chips cost, and so it's not a big deal. So I'm going to use these just because I think this circuit's easier to understand. But if you want to experiment with something else, you can. And actually, if you want to try to come up with a better circuit here, I didn't spend a whole lot of time on this, and I got it down to 7 gates. But maybe you can do better. So maybe something to think about. Okay, so I wired it all up here. So we've got our 74LS04, our 74.
Okay, we got our work cut out for us. That's for sure. Okay, so we'll start to make those in a second.
LS08 and our 74LS. Maybe something to think about. Okay, so I wired it all up here. So we've got our 74LS04.
Okay, so the 04 starts on $37. What do you say, 04?
Our 74LS08 and our 74LS32. LS04, our 74LS.
Okay, 4 goes on 37. That is 37. Okay. All right.
S08 and our 70.
The 08 starts on 46. And we're going to need to take this. This or something. Okay, it should be fine. And then on 55, we have the 32. I'm gonna write this down. The 04 74 LS 04 is inverters, is not. 74 LS 08 is and 74 LS 32 is or. Okay, cool.
For LS32, all hooked up here. And you can see I hooked up the power pin to pin 14 and the ground to pin 8 or pin 7 for all of these. And that's how they all are. If we look at the data sheet for 74LS04, for example, you can see power pin 14, ground is pin 7, and it's got the 6 inverters on there. We're only using 2 of them. And then the same thing for our AND gate. This is the 74LS08, and you can see it's got power and ground, and then it's got the 4 AND gates. We're only using 3 of them on there. So if we kind of follow this through just to make sure it all looks right, the output of our select here, so when we push our select button, that output, of course, is on pin 3.
Silly.
Isn't that hilarious?
Yeah. Poor mom. She's so exhausted. You should have put a blanket over her.
No.
Alex, she doesn't like sleeping in her bed during the daytime. Or she slept in your bed that one time.
Yeah. Alright, so let's get to it. I'm gonna get power onto this, onto all of our chips. Okay. Heating up. Heating up. Okay. Okay, we got the powers. Now let's get the grounds. Am I on the right thing? Okay, good. Okay, so we got the power for all of these. Now we need to do some adjustment. That seems good. So the only thing that I can see here, I'm gonna move this over, and then now we have a clean line there. And so let me write down the circuit. Okay, so we have the okay, so the first gate is the astable and the select go to an AND. Okay, so we have the schematic written down. So the first thing we're going to do, we're just going to do this step by step. I will confirm with his, but the first thing we want to do is we want to take the output of the astable and go to the, so we need to remember that this is the NOT, this is the AND, and this is the OR. So we need to connect the select, which is this output, to an AND gate. So we need to look at the pinout for the AND gate. So if we go to the LS or 74 LS08, which is the AND gate, we can see the pinout. So the output for one of these AND gates is like pin 3. So oh, I see. Okay, so what he's doing is, so let's get this first line in, I think. So let's try to move some of these out of the way. We actually ended up snipping these, but let's see what we can do here. So we're gonna take a green wire and send it to pin 2 of the AND gate. So we're gonna take the output of this first guy. Okay, and it's gonna come all the way down here. You want it to be really tight too. And it's gonna go to pin 2 of this AND gate. So if we want it to go into this hole, then we're gonna go 1, 2, and cut it. And then we're gonna squeeze it at where we need it to be. And then we can take this thing out and actually use it. Okay. Well done. All right. So now the interesting thing about this is that he's sort of chaining a net together. So the other part of this AND gate is the select, but the select is also going to a NOT gate. So first we're going to tie pin 1 of the AND to pin 1 of the NOT. Okay, so we want to, again, we want to use it in this pin, pin 1, so we're going to go 1, 2, and cut at the end of 2. Then I'm going to crimp it a little bit where we need it to be. And we can take it out. Okay, pin 1 to pin 1. Beautiful. And now we need to hook up pin 1 of this NOT gate to the output So I believe he moves the output down here. So it's a little bit cleaner. So we're going to take this output and put it onto there. Okay, great. So we're going to take our output. Okay. It's going to be kind of hard to get in here. So we want to connect it to this pin. So we go 1, 2. See if we can get in there. I forgot to squeeze it where it needs to be. Okay, kind of guessing there. Okay, seemed to work out. So this is pin 3 of the 555, which is the output, to pin 1 of this NOT gate, which subsequently goes to the same. So this bar ties together these two things, but saves you a wire. So this is going to be the output of our first AND gate. So this AND gate is going to go to OR. So first off, let's use the second. Let's use the second AND gate. The second AND gate is going to take the output of this NOT gate, which is pin 2, as the input. So it's going to be pin 4. So we're going to take pin 2 of this to pin 4 of this. So pin 2 of this. Damn it. Okay, pin 2 of this NOT gate to pin 4. So this is pin 4. So we're going to cut 1, 2, kind of 2.5. Oops. And then, I don't want to forget, but we want to squeeze it to mark where we want to actually strip the insulation off of this thing. Okay, pin 2, pin 4. Nice. It's so satisfying when it goes in nicely. Okay, the next step is, now that we need the output of the manual button. So we need this one. So we need this to go to input 5, which is going to be down here. So pin 5. Yeah, so pin 3 of the second 555 to pin 5 of the and chip. Okay, so pin 5 is right here. Pin 5 is right here, so we're going to go 1, 2. Then crimp it. Take this out. Let's see if we can get this. There we go. So we have pin 6 is our second AND output. So what we're going to want to do is we're going to feed these two outputs into an OR gate. So we're going to take pin 6 to pin 6 of the AND chip to pin 2 of the OR chip. Okay, good. What did I say? So the output of this thing, but he does it on the second row. So here goes to pin 2 of this chip. So pin 2 is right here. So let's go 1, 2, cut. Okay, there we go. Pin 2. Okay, now pin 1 is going to go to pin 3 of this. And actually, you know what he did though? Yeah, that should work. So now we have pin 3 is going to go to pin 1. So this is the second output, or the first output rather. Then we want to cut it right here. 1, 2. Okay, so we've just done, so now pin 3 of this is the OR gate. So this is actually going to go to the third AND gate. And we need to look at the pin out because I don't know what the outputs. Okay, so pin 8 of the AND gate is an output. So 9 and 10 are inputs. Okay, and then halt is an active low. Okay, good. So now we're going to use so wait, but actually we need to look at the pin out for this 04. So pin 8 is an output here. So we're going to just invert that. Okay. All right. So we're going to take the output of this bad boy and send it to 8, 9, 10. So this is 10. I'm going to go to here. Cut it. Cool. Now we have a really fancy one. We have the OR. We just need to take the output of this OR gate and get it over there. So I'm gonna actually get a pair of, I'm gonna get my phone and see if we have any needle nose. I'm gonna be right back. Okay, so I found two interesting tools. One are these ultra needle nose pliers, and they have a flat, which is what I was looking for. And then I found these curved ones, and I was thinking maybe I could get in there with this, but these seem perfect. The first thing we want to do is we want to just bend it, right? Okay. Then we want to bend it again. That should suffice. So now that we have this, we want to take the output, so that's pin 3. That's pin 3, so then 1, 2, cut. I'm going to try to, just for the fun of it, I'm going to try to improve this a little bit. I don't know how people make these like perfect right angled pieces. Okay, but this should just pop right in there. All right. Wow, check that out. Um,
There's a little bug digging into me.
oh no.
He's like poking at me.
Okay, so he didn't use a resistor. But I'm gonna use a resistor just in case. Oh, check this out. New innovation, by the way. So I held out. I had a pack of resistors in this like long sleeve thing that was really inaccessible. But the thing that was really nice about that resistor kit is that it had all of the nice...
I kept pausing and it wouldn't pause. I'm
No.
very sorry.
So there was this pack of resistors, but it was in a weird form factor. But what's really nice about it is that it had all the values that I actually need and not a bunch of unnecessary values. And I didn't sort those into my bins because I wanted to go. So I used one of my old boxes that had a bunch of resistors of random values in it. And now I have a portable resistors box.
Wow.
Because I like doing
Convenient.
electronics outside. It's much nicer to do it outside than in a freaking cave.
Yeah.
So...
You could just open up the garage doors and...
No, but I like to be under the cover of sun. Or I'd like to be whatever.
There's no sun.
I like to be in the sun. No, but I mean
Yeah.
under the sky. I feel like there's a deep psychological thing. Who is it that said, never trust a thought
Never trust
you
a
have...
thought.
Never trust a thought you have
Or a
indoors.
Who said never trust a thought or a Jew?
What?
Was that Chief Keef?
Don't.
I can say that.
Okay, so apparently the quote that "never trust a thought you have indoors" is not meant how I mean it, but I'm gonna repurpose it and say that never trust a thought that you have indoors.
Okay.
Wait. All right, so let's test this thing out. Uh-oh. So this should be lighting up. So let's make... So what we can do is we can start to just analyze the logic. So wait, we need to tie this low. That's part of the problem. So let's just do this really quickly. Oh yeah. All right, so we have the clock synced up to the A-stable 555. But now if I switch the mode, I should be able to single step. All right, we did it.
I'm gonna get my hoodie.
Okay, so that completes the Ben Eater clock. You know what? I think I'm gonna post on TikTok. I haven't posted on TikTok in forever. All right. I'm just going to record a little video. And then I can get started on finishing the PCB. Okay. Okay, so this is Ben Eater's clock module. It has a couple of things. There's 3 555 timers that are all sort of used in a different way. The first one is used in an astable configuration where it basically turns high and low in a set interval that can be modulated, so I can turn up or slow down the clock. The second mode is a button where I can manually turn something on and off. And the 555 is really only needed for debouncing. So it uses the SR latch that's just built into the thing. I don't know why I was doing that. And then the last thing is this switch that basically just uses the SR latch, and I can turn it on and off. And so what this output does is it uses a couple of logic gates. You know what? I need to redo this. Okay, this is Ben Eater's clock module, and it uses 3 555 timers in different ways, and then a couple of logic gates to combine the outputs here so that you can control your computer with a clock in 2 different modes. The 2 different modes are selected by this switch, so now the output of the clock is off, but there's a button here that lets me step the clock so that I could manually step my computer forward. Now the way that this astable configuration of the 555 works is that you have basically the 2 comparators inside of the 555 are used in a way that when a capacitor fills and discharges, it reaches the threshold in the basically the resistor divider network, the voltage divider network inside here. It's kind of a complicated way to say it, but it's actually simple if you look at a block diagram of the 555 on Wikipedia. Okay, but then this other configuration is actually really simple. So the only reason why we actually need a 555 for just a simple button is just for debouncing, so that we make sure that there's, you know, some amount of time that it takes for this capacitor to empty, so that we don't accidentally hit it multiple times. If you look at an oscilloscope, you can see that this is actually a problem, and that you definitely need, if you want to only step once, that you definitely need debouncing. This third 555 really sort of passes through all of the actual comparator logic and just uses pin 4 and I forget pin 2 to directly control the SR latch that's built into the 555. Then we have just a bunch of combinational logic to actually mux these together, basically. I'm almost done. We'll clean up in a second, then we
Oh
can.
no, that's totally fine. Looks pretty.
Yeah. The only thing that I could do better is I could cut the leads off of this to make them short so they don't stick out as high. That's what he did,
Yeah.
and it makes it look a lot neater.
Yeah, but I like it on the screen. Looks nice.
Yeah, I think it does look nice from top view.
Do you have coffee left?
Yeah, check the thing.
Okay. I'm gonna get a little bit because I'm still feeling really tired.
Yeah.
Okay.
If there isn't, we'll just mix them.
Yeah, and do you have more to do? So that's fine because I still could do more homework. I was doing some assignments, so I don't have to do them this week.
Yeah. Okay, maybe I'll do something for another hour or so.
No, you don't have to. I was just saying like I can.
Okay, yeah.
'Cause
Are you getting hungry though?
Kinda. But no, I was just saying like all my assignments are done, but I can keep doing like future assignments is what I was saying if you had more work to do. Because I'm here, I don't want to take away from your tinkering time.
Yeah. Yeah, I kind of wanted to hop on KiCad for a bit. I want to show you my actually.
Okay, well, I'm gonna go get some coffee.
Okay, yeah, get
and
some
then
coffee.
I'll
Yeah, let
come
me do
back
this.
And we can keep doing whatever.
meters clock module, and it uses 3 555 timers in different ways, and then a couple of logic gates to combine the outputs here so that you can control your computer with a clock in 2 different modes. The 2 different modes are selected by this switch, so now the output of the clock is off, but there's a button here that lets me step the clock so that I could manually step my computer forward. Now the way that this astable configuration of the 555 works is that you have basically the 2 comparators inside of the 555 are used in a way that when a capacitor fills and discharges, it reaches the threshold in the basically the resistor divider network, the voltage divider network inside here. It's kind of a complicated way to say it, but it's actually simple if you look at a block diagram of the 555 on Wikipedia. Okay, but then this other configuration is actually really simple. So the only reason why we actually need a 555 for just a simple button is just for debouncing, so that we make sure that there's, you know, some amount of time that it takes for this capacitor to empty, so that we don't accidentally hit it multiple times. If you look at an oscilloscope, you can see that this is actually a problem, and that you definitely need, if you want to only step once, that you definitely need debouncing. This third 555 really sort of passes through all of the actual comparator logic. It just uses pin 4 and I forget pin 2 to directly control the SR latch that's built into the 555. Then we have just a bunch of combinational logic to actually mux these together, basically. This is Ben Eater's clock module, and it uses This is Ben Eater's clock module, and it uses 3 555 timers in different ways, and then a couple of logic gates to combine the outputs here so that you can control your computer with a clock in 2 different modes. The 2 different modes are selected by this switch, so now the output of the clock is off, but there's a button here that lets me step the clock so that I could manually step my computer forward. Now the way that this astable configuration of the 555 works is that you have... Alright, so I got it all posted. Okay, so that's great. So now, I guess we can end this because this is done. The only thing I can do is clean up these leads, but I don't really feel the need to do that, honestly. Because the next plan of this is just to put this onto a PCB. So, alright, I'm going to end the stream now.